Okay, we start up again. To understand the boundary conditions, of course, essential to describe any problem, you have to understand the layout, the geometry. And here is a couple of choices then that has been made, how the mesh system is arranged. So it was a rectangular mesh system, 2 dimensions, and you have been given 1 by 1 non-dimensional in size. So this is the computational domain. And then we divide this one up in so and so many internal cells, something like this, 4 by 4 internal cells. And then we add an additional layer on the outside. Ghost cells, fixture cells. So inside here you will find the boundary conditions. Same cell system here. And then we start numbering. I want n by n internal cells. Hence we are going to number them like this. 1, 2, yada yada yada, all the way up to n plus 2. And that goes in I and j direction. If you look upon it as discrete values, not tensor notation with I and j anymore. So that is the overall geometry. And then we have to choose for one single cell. Here, this is cell number I and j. Where are my unknown located? That is a choice. Sort of the obvious choice, put all of them, 2 velocities and a pressure in the same point. Yes, you can do that, but if you can recall the Navier-Stokes, for the velocity, it was a pressure gradient, a derivative of the pressure. So say we have all of them in the center, collocated mesh. Finding the new velocity there will involve including a pressure gradient, derivative of the pressure, central scheme. Then you have to use these 2 pressures. The sad thing then is that the pressure where you're standing doesn't enter into the equations. And then you run into problems with a pressure field, like a sort of a checkerboard pattern, 2 separate pressure fields that doesn't talk to each other. Very strange results. So that was sort of the first pain that people started fighting with, how to solve this one more consistent, so you don't have this pressure nonsense. And what we are using here is something called MAC, marker and cell. That is a staggered mesh system by Harlow and Welch in the mid-60s. They wrote an article where they wanted to simulate free surface. And they used a marker inside a cell, just a dot indicating whether this was a live cell, if it was liquid or gas, water or air. So that was their idea. So they called the system MAC, marker and cell. But the gold in that article was not this marker thing. The gold was the mesh system that they chose. They said like this: in the center I have the pressure. The velocities, they are located on the mid surfaces. Here you will have U, I, J. Up here you will have V, I, J. That one made the discretization star very neat and compact. Very nice indeed. Here, of course, is a choice. Should I have U, I, J to the left and to the right? Your choice. They chose it to the right. That means the velocity here, what will he be? Well, he must be U, I minus 1, J. And down here, what will the velocity be? Well, that must be V, ij minus 1. So that is the staggered mesh system. And for instance now, think of the divergence for one single cell. Remember, we are solving the Poisson equation for the pressure. Then we are focusing sort of in the center point. And the divergence for one cell has to be included into the SOR, the sort of deciding if the iteration has found a solution or not. So what about the divergence? Well, you will now write it as the following. Du dx will be this one, uij minus ui minus 1 j divided by delta x, or h if you like. And then you do the same in the y direction. Vij minus 1 over delta y. And you find exactly this recipe in the Solar code for the divergence. So it's a very compact scheme, compact discretization star. Nowadays you have more modern techniques to avoid this pressure trouble. So a collocated mesh is more and more common actually, because here is a lot of bookkeeping, some additional trouble typically when you are looking at the boundary conditions. So let's have a peek at the boundary conditions. Any questions to this one? That's okay. It's sort of a choice how to do it or how not to do it. So let's see. The boundary conditions that has been implemented here. First, for all j's, okay? So that means, well, sorry, I have to start that one. Here we go. Here we are. For all j's, that's the first loop. And then we are looking at the boundary conditions alongside this wall and this wall. Now, for the square cavity test case, both of them are solid walls. So for the horizontal velocity, that's fairly simple. He must be 0. And you see here, the velocity there is located actually on the wall. And that should now be for I number 1. So u of I number 1 has to be 0. And indeed it is. But what about v? Well, he is not said to be 0. What's this nonsense? Well, remember the v velocities, they are located half a cell inside the solid wall. They are put here. And being an elliptic problem, you have to specify the velocities all around. That's an elliptic problem for you. You need boundary conditions all around your computational domain. So you have to say something about this velocity. You know that it should be 0 on the wall, no slip condition. Okay, then we say if I have a velocity inside my domain, this one has to be calculated, then I construct a boundary value so that I get 0 in between them, halfway. That's the trick. So you set this one to be minus the one inside. And same on this side, create a velocity here. If you had something inside, okay, then you want to have a 0 midway. So that is what's been done here. Here, trick, un plus 1 has been specified to be 0, but here it's vn plus 2. How come? Why not n plus 2 for both of them? Well, that's due to the staggering system. Remember the cell number n plus 2, that's the last cell row here. And where is u located? Well, un plus 2, he's actually located here, at this location. But that one, is not part of the problem. He's never used, he's never addressed. You have to specify this one belonging to this cell. That's n+1. So for U, okay, then the boundary condition is for n+1. But for V, then it's n+2. He's half a cell inside the wall. So here, to be able to understand these boundary conditions, you need this figure and this one quite clear in front of you, or else you are lost in the bookkeeping. For the x direction, for all i's, okay, it's fairly the same, just skipped 90 degrees. For the cell here, number 1, of course we specify the v velocity here has to be 0. It's a solid wall. And the u velocity, you have to say something about him. Well, he is minus whatever you have inside, so you get 0 halfway. Exactly the same there. For the top wall, well, for the velocity in the y direction, this is a solid wall, so the velocity here, v velocity there, has to be 0. And that is v, not n+2, but the one below, n+1. So that one has to be specified, v n+1. And indeed it has been. While the u, now here's a trick, u n+2 has to be specified. That's the velocity up here, half a cell above the wall that is moving. Okay, what should he be? Well, the wall should be moving with a velocity of 1. That's the square cavity test case. So if you have a velocity inside here, you create the one inside, half a cell inside the wall, so that you get the average velocity in between them to be 1. Hence, you have the number +2 here, added here. Okay, that was the boundary conditions. Any questions to those? In the exercise 12, you are going to have to calculate the vorticity, the curl, for each cell. So clearly you're going to need those two figures very, very clear in front of you, or else you are lost. Now let's play around with the geometry. I want to simulate the following. The flow between two parallel plates. Both of them are standing still. Then I send in a constant velocity profile, u equals 1, non-dimensional. Then I want the entrance length to be done with, so I want a fully developed flow on the other side. So the velocity profile here should be then the Poisson formula. That is what I want. How can you get that one? Well, remember, it's a 1-by-1 computational domain. So if you are going to do this, imagine yourself 1-by-1 meter, send in a constant velocity profile, and you want to have it fully developed on the other side. That's very narrow indeed. So the fluid there has to be honey or asphalt or something very, very sticky indeed. Because what I want is the boundary layer to grow and the boundary layer to grow, and they should meet in the center before the exit. So well, we can try here with a Reynolds number of 1,000, but I think we are in trouble. But now that means we have to rewrite the boundary conditions. In the x direction here, for all the i's, well, they are still two solid walls. The only difference now is that the top wall is not moving, so I just remove the +2. That should be it. So now we have the case where no wall are moving. For the inlet here, for all the J's, here clearly we have to do something. So what will we have on the inlet? Well, I want a constant velocity profile at the inlet. That should be u number 1. He's not 0 anymore, he should be 1. Okay, and the v velocity, he should be 0. What about on the other side, on the outlet? Well, on the outlet, actually, I have no idea. So what do? We use a Neumann condition, just saying the derivative equal to 0. So then I have trouble finding the derivative just at the outlet. So there I cheat. I say the derivative here should be 0 for the u velocity. For the v velocity, that's okay. Saying the derivative is 0, that will actually be on the outlet boundary perfectly when you think in terms of a central space differencing, half a cell away. But for the u, it will be half a cell inside the computational domain. I do it, I know it's wrong, but should be here somewhere. U n plus 1 equals u to the left, u n 1, not comma, like that. Then I have a derivative equal to 0, actually half a cell inside the domain, but never mind. For v, I just put these two equal. So the philosophy will be as follows.
Should it be for all the j's, not for one?
For all the j's? Oh yes, thank you, thank you. Clearly that one was wrong. Thanks. So the philosophy will be as follows. You do something wrong on the outlet here in this region. You're sort of now demanding that the streamlines should be horizontal. That might be enforcing something unphysical into the problem. But if my entrance length has been overcome and the flow is fully developed, then that should be correct. If it's not correct, okay, I do something wrong here in this region, but the error should not propagate too far upstream. So the solution in the main part of my domain should be okay anyway. That's sort of the philosophy. Let's try this one and see what happens. We hit run and then I get a warning. Delta t should be smaller than, I don't care, I run anyway. Yeah, he seems to be running. Now, these graphs is of course nonsense. The stream function, that's not what I hoped for. How should the streamlines go? They should be something like this. So in the right half should be parallel, but clearly in the left part they have to tend towards the center. So no, this one can't be correct. What about the pressure? Well, that's clearly wrong. How can you tell? If it is fully developed, what does the pressure look like? Then you will have a constant pressure gradient in the x direction. Then the pressure contours should be lines like this. Then it's fully developed. Here, of course, you will have high pressure in these corners because you are going to push the velocity towards the center. So that's okay, but the right-hand side of that graph has to be rubbish. And here the velocity vectors, only horizontal. So Reynolds number 1000, no way, no way. So I change it to Reynolds number, say, 1. Try to run it. And then all of a sudden he demands the delta t should be very small. Why? Now the Reynolds number is very low. It's extremely viscous fluid, very sticky, like honey. That means he should develop much faster in time and in space. Well, if that's going to happen, then you're going to need a smaller delta t to describe all that's happening within a much more narrow time space or time window. You see what happens here? He crashes sort of instantly. So that one is definitely not good. You have to use a very small time step here. So let's put in a couple of zeros, but then my maximum time should be quite small. It should happen quite fast actually. Take a time limit of 1 and see if this one runs. Yeah, seems to be running okay. And also as an indication, you don't have many pressure iterations here at the end. That means nothing much happens from one time step to the next. Should indicate that we have a sort of a steady state situation. So we remove these. Now I have a streamline pattern that I can believe. Horizontal lines in the right part, and then sort of a contradiction here in the left part. The pressure, beautiful. High pressure in the corners, and then a constant pressure gradient to the left. That one looks much better. And here the velocity. Yeah, well, you send in a flat profile, but quite rapidly you see you will have here a negative v velocity, here a positive one. So you can sort of see the boundary layer actually growing here, and should then meet roughly in the center. So that is another case for the same code. Just rewrite the boundary conditions, and then you can do whatever you want. Any questions to that one? Okay, let us try once more. Say, go back to Reynolds number 1000, when we had some, say 200 here, and again increase the time step. What I want to do now is the same geometry. Like that. But now the top wall and the bottom wall, they should be not solid walls. They should be symmetry lines. That means you can have a slip velocity alongside these walls. So they can be streamlines with a velocity bigger than 0. You are not allowed to have velocities through these two, but they will sort of be just symmetry lines. Then we send in constant velocity, but not in the center part here. On the outlet, I have, again, no idea, so I say du dx equal to 0. Same goes with the v component, the v dx. So let's try that one. Now I have n equals 20, so it's not that many. We can try anyway. So here we have the boundary. V is set to be 1, that's okay. U is 1. V is 0, that's okay. But I now say U for let's say, what should we take from 16 up to 22 or something. equals 0. Then I will have this center region with 0 velocity. The V, that is said to be 0. For the outlet, you have a derivative equal to 0. That's okay. Now for the slip walls, how can we create those? Well, the V velocity should still be 0. No velocity straight through a streamline. But the U velocities, they should now be the same. So you just remove the minus. There you have symmetry lines instead. Now let's try this one and see what happens. He wants a smaller one. I skip that and force him to simulate anyway. Of course, the comparisons here, they don't match. Streamlines, just straight lines. That was not what I hoped for. Pressure looks very strange, doesn't it? But remember, you haven't given the scale for the pressure. So if you hit the plus button here and somewhere in the field, you can actually read the level. And here the level is roughly 0. So the pressure is pretty close to constant either way. The velocity field here fairly constant. So I wonder, has he actually understood what I meant? He should. Ah, no, of course not. Sorry. That was U number 1, of course. Let's run once more. Ah, that's more like it. He crashes. Okay, we need smaller delta T. We try with 1. Yeah. Ah, he's on the limit. You see, he uses... now it's okay. It's fewer and fewer pressure iterations, but he had some problem initially. Stream function looks a little strange. Pressure now a little bit different, and the velocity, well, I put the 0 a little bit too high. Let's put him more in the center and try again. Let's say from 8 to 12 or something. Yes, a little trouble, but hopefully he survives. Yeah, it doesn't explode, but he uses roughly 300 iterations for every single time step, as you can see. And why is that? So here you have a problem which then will not involve a steady state situation. You send in constant velocity around a solid wall, and then of course you will have this vortex street like that. The Reynolds number is 1000 based on this distance. It will be some hundreds based on this one. So it will be this oscillating vortex shedding. And he should stop at 100, I hope. No, I had the 200. That takes too long. Let's stop him after, say, 20. I think that's enough. There we go. So there you have the streamline, and yes, you have some indication here. Some vortices has been shed, and the pressure, he will typically then be high pressure, low pressure, alternating from the vortex shedding, and the velocity field here looking something like this. Zero velocity here in the center region, and then you will have this wavy velocity pattern downstream. It's not easy to obtain here when you may have a 1-by-1 computational domain, but as you see, it's actually possible. Here, of course, we can't really believe the boundary conditions at the outlet, because clearly the velocity field is not going to be with a parallel velocity streamlines at the outlet. No way, you can't do that. Then you have to have a very, very long computational domain. So maybe what we should have done was maybe something like this, a higher order Neumann condition there at the outlet. That would be better. But as I said, the philosophy will be, we do something wrong on the outlet, but hopefully that error doesn't propagate too far upstream. So that means we can believe the simulation in the main part of the domain. So that's the philosophy. Okay, that was some playing around with the Sola code. Any questions to that one? No? Okay, then I just wish you good luck with the exercise 12. And the exam, of course. We stop here.